Today we're going to talk about Chapter 4, Module 4, Advanced Cryptography. So we're going to learn about what are called digital certificates, and we're going to describe the components of public key infrastructure, and you want to be able to list the secure communication and transport protocols that are used, and explain how to implement cryptography. So, starting off with digital certificates. A digital signature is used to prove the document originated from a valid sender. Just like you put your signature on a document, on a check or on a credit card receipt or whatever. It proves that you signed that. So there's a weakness with a digital signature. It can only prove that the private key of the sender was used to encrypt the digital signature. So think about that for a minute. Does that mean it can be forged? Well, if the hacker is clever enough and has the right information, yeah, it could be. There's a weakness in that's important. So an imposter could pose a public key under a sender's name. A trusted third party then can be used to help solve the problem of verifying identity. So that way we can ensure, is this actually John Doe's signature here on this document? How do we know? If someone presents a document that says this identifies me, well, how do we know? Did they just sign this document? So that trusted third party, what would that be? Well, if you live in Ohio, or if you live in any state and you drive, you have a driver's license. That's a state-issued ID that you went to obtain when you applied for your driver's license. That proves you are who you say you are. Usually has your address on there, the date that it was issued and the date it expires, and so forth. Your YSU student ID is another example of that. It has your name, your YSU Y number on it. Okay. So those are third-party IDs that can be used to help solve the problem of verifying identity. You have a social security card, your library card, your passport, and things like that. So a digital certificate is a technology used to associate a user's identity to a public key that has been, quote, digitally signed by a trusted third party. Okay, digitally signed by a trusted third party. So you see here in this picture, Bob wants to get a, he's going to use, Bob's public key is being used to buy a stock. Bob creates and sends a real message. Okay. Mallory intercepts the message and creates an imposter key. And this is one of the weaknesses in that. And then Mallory sends a different message, sell the stock now. Alice receives the imposter's public key and thinking it's actually from Bob, and ends up selling it, and then Bob's in trouble. Instead of buying it, he's selling stock. But the digital certificate would, ensure that Alice knows that it's actually Bob and not Mallory that's sending that information. So you have the Ohio driver's license, you have your YSU student ID, you have your social security number, your social security card. Each of those is maintained by those respective entities. So when you go to apply for your driver's license, you go to the Bureau of Motor Vehicles. When you apply for your YSU ID, you go to YSU's, the registrar's office. So a certificate authority is an entity that and the tools for managing certificates. They are the ones that do that. So, like the Bureau of Motor Vehicles uh, is that certificate authority that issues your driver's license. Okay. If a user wants a digital certificate after generating a public and private key, the users must complete the request. The user electronically signs it by affixing their public key and sends it to a registration authority, or RA, that's responsible for verifying the authenticity of that user. Once verified, it's transferred to an intermediate certificate authority, or CA, where the request is processed and a digital certificate is issued, a process known as certificate signing requests, or CSR. Okay. Intermediate CAs then are subordinate entities designed to handle specific CA tasks, such as processing certificate requests and verifying the identity of an individual. The person requesting that digital certificate then can be authenticated by the following methods: email, documents, or in person. Okay. Once they have that, just like your driver's license, you can then show that to any authority that's requesting it and say that, yeah, this is me. And it proves that you are who you say you are by virtue of the fact that the Bureau of Motor Vehicles or has issued you that driver's license and they've done the background check. So a certificate repository, or CR, it's a publicly accessible centralized directory of digital certificates used to view certificate statuses. This directory then can be managed locally by setting it up as a storage area connected to the CA server. Some circumstances might cause a certificate to be revoked, such as the following. Maybe the certificate is no longer used. So maybe the details of the certificate have changed, such as the user's address. The private key has been lost or exposed, or suspected to lost or exposed. Because then you have what's called a certificate revocation list. It's a list of digital certificates that have been revoked. Okay. So you have an online certificate status protocol performing a real-time lookup of the certificate status. The browser sends the certificate's information to a trusted entity known as an OSCP responder. Then that replies or provides immediate revocation information on that certificate if need be. And the OSCP stapling is a variation of the OSCP where web servers send inquiries to the OSCP responder server at regular intervals to receive a signed timestamp response. Kind of like your EasyPass transponder, so that when you run low on money, your EasyPass account is in suspended or inactive mode until you pay the balance. So that's updated every day, and all the toll booths along the way get that information. Okay, then so if you bring your balance down low, it usually takes 1 day for everybody to get updated that your account is active again. So here's an example of an OSCP stapling. Your web browser, step 1, I want to connect. The web server sends information, is that certificate valid? It checks with the OSCP responder. Yes, there's a signed approval. Send it back to the web server. Here's the approval, approved. And usually then it allows the transaction to proceed. There are different types of digital certificates. The most common categories of digital certificates are what are called root certificates, domain certificates, and hardware/software certificates. The process of verifying a digital certificate is, if it's a genuine, depends upon what's called the certificate chaining. The beginning point of the chain is known as a root digital certificate and is created and verified by that CA. Remember that we talked about that earlier. They're self-signed and do not depend upon any high-level authority. The endpoint of that chain is the user digital certificate itself. So here's an example. You can see in certificate you have Sectigo AAA, User Trust RSA Certification Authority, in common RSA Server CA email wku.edu. So most digital certificates are web server digital certificates used by your browser to validate that a web server is secure and is valid and not bogus. Web server digital certificates perform two primary functions. They ensure the authenticity of the web server to the client. They ensure the authenticity of the cryptographic connection to the web server. There are several types of domain digital certificates: domain validation digital certificates, extended validation EV digital certificates, wildcard digital certificates, and subject alternative name digital certificates. So here's an example. The web browser goes to client hello, the web server sends back server hello, and the algorithms are supported. Server digital certificate. You have your client key exchange, and then the pre-master secret. And then after that, we create the master secret and the session keys, and the process begins. Well, the conversation begins, rather. So you have your hardware and software digital certificates. You have your machine's computer digital certificates, code signing digital certificate, and email digital certificates. Oftentimes we don't realize all these things are running around in the background, securing everything. So there are digital certificate attributes and formats. There's a standard format called the X.509 version 3. Several certificate attributes make up an X.509 digital certificate, including the following: the certificate warranty period, end host identity information, encryption keys that will be used for secure communications, the signature of the issuing CA, and the common name or CN for the device being protected. Okay, so here's our knowledge check. What is a technology used to associate a user's identity to a public key and has been digitally signed by a trusted third party? A technology used to associate, so it's not the user's identity or the public key, but it's that technology. Looking at these, if we looked from the bottom, D would probably not be it because that's a repository. C is probably not going to be it because that's not one of the things we talked about. It's going to be either A or B. And when you think about that, to be able to associate a user's identity to a public key is probably not going to be A. More likely it's going to be B, digital certificate. And that's what it is. It's a technology used to associate a user's identity to a public key and it's been digitally signed by a trusted third party. Always think of your driver's license or think of your YSU ID. Okay? So it's a digital certificate. So what is public key infrastructure, or PKI? There's a need for a consistent means to manage digital certificates. That's where your public key infrastructure comes in. It's a framework for all entities involved in digital certificates. It's a set of software, hardware, processes, procedures, and policies that are needed to create, manage, distribute, use, store, and revoke digital certificates across large user populations. So again, it's a set of software, hardware, processes, procedures, and policies that are needed to create, manage, distribute, use, store, and revoke digital certificates across large user populations. So you have what are called trust models. Trust is defined as the confidence in or reliance on another person or entity. So you have your trust model refers to the type of trust relationship that can exist between individuals and entities. Direct trust is a type of trust model where one person knows the other person. Third-party trust refers to a situation where two individuals trust each other because each trusts a third party. So, if, for example, going back, if we use two students from YSU, they each show their YSU ID, and then they can trust each other because they have been verified by that third party, in this case, YSU. The web of trust model is based on direct trust, where each user signs a digital certificate, then exchanges certificates with all other users. The hierarchical trust model assigns a single hierarchy with one master CA called the root. The root signs all digital certificate authorities with a single key. The distributed trust model has multiple CAs that sign digital certificates. This eliminates the limitations of the hierarchical trust model. The bridge trust model is similar to the distributed trust model. One CA acts as a facilitator to interconnect all other CAs and allows the different models to be linked together. So here's an example of the different certificates and the public keys tied together to that certificate authority. This is a hierarchical trust model. This is a distributed trust model. You have your certificate authority at the top. You have your intermediate CAs. In case the first one has 3 digital certificates, the second intermediate CA has 2 digital certificates that it manages. And lastly, the bridge trust model. So you can see, again, you have the certificate authority at the top with its 3 digital certificates. You have a bridge CA here to the right that connects the top certificate authority to the bottom certificate authority. That bottom certificate authority then has 2 intermediate certificate authorities. The one on the left has 3 certificates. The one on the right, 2 certificates. That's a bridge trust model. Okay, so with these PKIs, a certificate policy, or CP, is a published list of rules that govern operation of a PKI. The CP provides recommended baseline security requirements for the use of and the operation of CA, RA, and other PKI components. Remember, CA is your certificate authority, your RA is your registration authority. A certificate practice statement is a technical document that describes in detail how the CA uses and manages certificates. It also covers how to register for digital certificates, how to issue them, when to revoke them, and procedural controls and key pair management. Okay, so the life cycle of a certificate is typically divided into the following 4 parts: the creation, suspension, revocation, and expiration. So if you think about that, the creation is when it's created and then it's implemented and put into use. If something goes wrong and they need to halt the use of that, that's where suspension is. So it's only suspended, it's not canceled or revoked. Okay. And then this third one is revocation, so it's been revoked. That means it can no longer be used again. if need be, a new one had to be generated. And then lastly, the fourth one is just a simple expiration. So if it's just for 1 year, the year is up, we have to go get another one. It's not been suspended, it's not been revoked, it just expired through normal processes. So your key management is an important concept. Your public keys, they can be stored by embedding them with the digital certificates. The private keys can be stored on the user's local system. Software-based storage may expose key to attackers, which storing your keys in like a key locker and things like that, or anywhere on the computer, is highly, I highly discouraged from that, because again, it could be easily hacked and getting into. You have your multiple pairs of dual keys can be created. One pair used to encrypt information, and public key can be backed up in another location. The second pair would be used for digital signatures, and the public key in that pair would never be backed up. So you have the following procedures can help ensure keys are handled properly. Escrow, that's like when you go in buying a house, you put the house or the money in the escrow. You have expiration, renewal, revocation, recovery, suspension, and destruction. So you make sure that the keys are handled properly. So if it's time to retire the key, then you should not suspend it, but you should revoke it. Okay. And think of with each one of these terms how it works related to the keys. So here's a case called M of N control. So you have your part 1, part 2, part 3, part 1, part 2, part 3. In the N group, M is a subsidiary group. So that set of keys have to be maintained. Alright, so here's our check activity. DAG wants to set up a trust model in which he only will serve as a CA. Which trust model would he choose? The bridge, the distributed, the hierarchical, or the sole trust? And take a minute to think about this. So if we look at this, it's a trust model. They're all trust models. So he will only serve as a CA. So is it bridge, distributed, hierarchical, or sole trust? Okay, so it's a hierarchical trust model. This one CA is responsible for only the digital certificates for that organization. Okay, you have your secure communications and transport protocols. Cryptographic algorithms are used to protect data in transit. Okay, it's important. There are different secure communication and transport protocols based on the cryptographic algorithms for protecting data in transit. Okay, remember that these protocols typically rely on encapsulating or enveloping the data to be transmitted inside something else, in this case like tunneling. So the following protocols use tunneling: your transport layer security, otherwise TLS, and your IP security, IPSCC. So for the transport layer security, it's a replacement for that. It's a replacement for that original secure sockets layer, or SSL, and provides a higher degree of protection. Current version is TLS version 1.3. A cipher suite is a named combination of the encryption authentication and message authentication code algorithms that are used within TLS. For IP security, it's a protocol suite for securing IP communications. IPsec is considered to be a transparent security protocol. It's transparent to applications, to users, and software. It provides three areas of protection that correspond with the three IPsec protocols: authentication, confidentiality, and key management. Almost sounded like the CIA, but this one deviates and we have the key management. The IPsec supports two encryption modes: transport mode and tunneling mode. Okay, and there are other protocols. In the secure version of the HTTP, actually plain HTTP is sent over the TLS and it's called Hypertext Transport Protocol Secure. So when you go to HTTPS, you're sending your plain text over a secure channel. And it uses port 443 instead of the port 80, which normally is HTTP. You have your secure shell. It's an encrypted alternative to the Telnet protocol used to access remote computers. You have your secure multi-purpose internet and mail exchange, SMIME. And it's a protocol to securing email messages. You have your secure real-time transport protocol, SRTP, which is a secure extension protecting transmission using the real-time transport protocol. So to implement cryptography, you need to, establish the following things. Cryptography that's improperly applied can lead to vulnerabilities. Remember in the previous chapter we had attack vectors. Well, if it's improperly applied, this vulnerability can be an attack vector. It's essential to understand the different options that relate to cryptography. Implementing cryptography includes understanding the following: key strength. So if you use PASS for a password versus password or supercalifragilisticexpialidocious, the longer the password, the better. So you also understand secret algorithms and block cipher modes of operation. Your key strength is important. The cryptographic key is a value that serves as an input to an algorithm. It transforms plain text into ciphertext and vice versa for decryption. So the following are primary characteristics that determine the resiliency of the key to attack, called key strength: randomness, crypto period, the length of time for which that key is authorized for use, and then the actual length of the key. Your secret algorithms. Keys must be kept secret, so does the same apply to algorithms? Yes. Would a secret algorithm enhance security the same way as keeping a key password secret? No. For cryptography to be useful, it needs to be widespread. A military force that uses cryptography must allow many users to know of its existence to use it. So you have your block cipher modes of operation. A block cipher manipulates an entire block of plain text at one time. Each block is encrypted independently. A block cipher mode of operation specifies how the block ciphers should handle these blocks. Some of the most common ones are electronic codebook, cipher block chaining, counter, and Galois counter. So here's another check activity. Which of the following is the most comprehensive secure communication and transport protocol? Note the word transport protocol. So we know SSL was replaced by TLS, so A is wrong. B is transport layer security. C is IPsec, and D is HSS. So when you think about it, it's going to be your IPsec, although you might have thought it's TLS, but the IPsec is considered more robust than TLS. This is because it provides security to IP, which is the basis for all other TCP/IP protocols. And protecting the IP, IPsec is essentially protecting everything else in the TCP/IP as well. So sometimes this might be considered it might be tricky when you think about that, but it's IPsec's the answer to that. Okay, so we're reaching the end of this chapter, and we should be able to define digital certificates, describe the components of public key infrastructure, list the secure communication and transport protocols, and explain how to implement cryptography. Okay? And this is the end of the chapter. Okay? And again, if you're not sure about any of these concepts or topics, go back and read them over again. Practice, or rather, learning is repetition under the condition of practice. So do it again and again and again and again. And as you do, you'll become better at it. Alright, that's it for this chapter section. I'll see you in the next chapter. Have a nice day.